something like this, right? This one. Go ahead.
Do you know what to do if your drink didn't come through and you swipe the card already?
No, I have no idea.
Which that means.
Oh, I'm sorry. I have no idea.
George, police already got home for GC.
No, they're always here.
Okay.
Is that like an example of the game?
Yeah, that's what we're talking about. That's what the exponential will do, right? So the exponential then decays it, right? So then you put the sign, you put a exponential that's gonna dissipate it, and then it looks like a sine wave.
Give me your login, and I'll go into your phone and see if I can do it. Okay. I was gonna take it to the yeah, I heard it's like a
I want to talk about triangles, and then I think we'll be ready to do the work. I might be missing something, but we'll find it. We're ready? All right, so it thinks I'm still recording? It can't believe that. I guess it does think I'm recording. Okay, I must accidentally hit the button. All right, so I have defined all these things in terms of circles. There is an obvious triangle definition of sines and cosines that we have learned before, right? Opposite over hypotenuse, all that stuff. What's opposite over hypotenuse? That's the...
Is this 5.2?
This is 5.2, yeah. What's opposite over hypotenuse? Okay, good. Okay, so I'll take a right triangle. Oh, I should guess, let's put this in the right context. So again, so go ahead.
Can you change the color?
I was wondering about green. Whether people like green or not. Purple's my favorite, but I didn't want to overuse it. All right, so I got a triangle. So pre-calculus is usually some mixture of college algebra and what we call trigonometry. Okay, so trigonometry has to do with the triangle, and so not only the trig functions, we call them trig functions, right? So we have these groups of mathematicians. Some people call sine and cosine circle functions. Some people call them trig functions, right? It just depends on whether you want to define them with the circle first or with the triangle. Now, it should be the case that even if I define them with I could have started this whole thing, and I have in my career, talking about the triangle definition first and then coming to the circle second, right? I've decided to start with the circle and then move to the triangle second, but the definitions should be the same, which is what we're about to show. As I mentioned before, we want to sine and cosine come up in that now they are going to help us solve this final issue with the triangle, that here we have A, B, and C, and we have little b, little a, and little c, and we know that a squared plus b squared equals c squared. There are about 500 or 600 proofs of that. And we know that, what about the angles? A plus b plus c? All the angles add up to 180, right? Let's demonstrate that super quick. If I take a triangle, I want to show that all the angles add up to 180. All right, we've been told that for some time, but maybe you don't believe me.
It's 5.2.
It is 5.2. All right, so the claim is that all the angles add up to 180. This is a triangle, right? So what do you need for a triangle? How many points? 3 points. But in particular, there's something special about these 3 points. They're not all on the same line. Okay, so in order to have a triangle, there has to be one point that's not on the same line as the other 2 points, right? That leads right into Euclid's fifth postulate that says that because this point is not on this line segment, there's one and only one line that goes to this point, which is parallel to this one. Okay, so there it is. There's one line that goes to this point, which is parallel to this. And oh my goodness, what is the measure of this angle? Here we have 2 parallel lines, and this is a transversal. This is C. What is this angle? A. What's this whole thing? 180. Questions?
Would it be 90 on 8?
We don't know what it is. We just know that A plus B plus C is the whole thing. And that's the proof. Okay. So the fact that all the angles add up to 180 degrees relies so heavily on the fifth postulate. Now the fifth postulate, so let's step back. Geometry starts with Euclid. Well, geometry of course starts before Euclid, but Euclid was the first person to say, look, I'm going to create mathematics from the bare bones of nothing. Right? So he comes up with 4 rules. He says a point is this, a line is this. Right? And then he adds a couple more constraints, right? And he says, from that, I want to build all of geometry, right? And he started trying to do that, right? And he needed this last one. He needed that if I give you a point and a line, if I give you a line and a point not on the line, and there's one and only one line parallel to it, he wanted to be able to prove that from the other 4 things, and he couldn't do it. And so he says, okay, I can't do that, so I need to make it the 5th rule of geometry that nobody questions. It's just what it is. And from those 5 things, we have all of Euclidean geometry.
So who made it again?
Euclid.
Euclid.
So from those 5 rules, we have all of Euclidean geometry. Now, he dies 2,000 years ago, right? And so then other people are just like, well, let me see if we can prove the fifth postulate. So all these mathematicians, the most brilliant people in the world, try to prove that it is the case that if I give you a line and a point not on the line, then there's only one line that goes to this point. And in the 1900s, Cohen showed that you can't prove that, and you can't not prove it. That rule is something that either you accept or you do not. Right? And so therefore, there's Euclidean geometry where you believe this, and there's non-Euclidean geometry where you don't believe this. And if you don't believe this, this means that you believe that there is no line that goes to this point, or you believe the other alternative, that there's more than one line that goes to this point, which is parallel. Now, of course, the response is, well, wait, why would you ever want to believe non-Euclidean geometry, right? And so one of the geniuses that uses non-Euclidean geometry is Einstein. So his view of the universe is that every line, even though every parallel line meets in one place, and it looks like that on this globe, right? When you look at longitudinal lines on the globe, locally they look parallel, but they all meet where? At the poles. So that's called spherical geometry, right? So the fifth postulate is something you accept or don't accept. And so mathematics has rules that either you accept or do not, right? And so when Cohen proved this unsettled everybody, because we really like to have thought that mathematics explains everything. And it does not. It does not. Right? So there's some things. So what Cohen showed was that if you take any arithmetical system, you create any system based on arithmetic, there are always going to be statements that are outside of the system that you can't prove or not prove. You either have to accept them or not. Right? That's the very, very troubling thing. Right? And of course, that was a lot of evidence for other people to come along and say, well, that clearly proves the existence of some other things, right? So anyway, so we have these two relationships between sides and angles, and now it's the time to start relating those two things. I want to be able to say that if I know some sides and some angles, I want to be able to relate the two things to each other. At this point, we have no way of relating a little a and capital B. so let's start doing that. And so in order to do that, I want to take a triangle. Oh, if there's any justice, hopefully, that is not what I wanted to copy. I forgot that I had already copied something. No, I don't want that one. I want this original one. I want that. I want this. So I'm going to copy that. I'm going to bring it back here, right? And I'm going to get rid of this. Yeah, I want to get rid of that. I want to put this back here, right? So what I want to do now is I want to take a triangle, and here's the triangle. So let me see if I can be better. Here's the triangle like this, right? Make this straight. That didn't work, I know. Right? So I'm going to take this thing, and then I'm going to is it going to give me the whole thing? It is. I want to take this thing and I want to put it here. Okay. I want to start talking about these angles. So this is the angle theta. Let's pretend that's straight. And so this is often called the side opposite theta, and it's the side adjacent to theta. Okay. I really want to use green. I'm not. I'm going to look at this triangle right here. So now I've got two triangles. These two triangles are related. What would we call these two triangles? Begins with an S. That's close. Like some hangman.
Well, you said S.
E? Nah, that don't count.
Why doesn't it count? What did you say?
Is it a Y?
No.
I?
Similarity?
Similar. These are similar triangles. Right. Now that's a street version term, but also it has something to do with proportions of sides, right? So that, what do I know about this point? This is X and Y, right? This point's X and Y, right? So I know that, and what's this distance here? What's this distance?
R.
Oh, but this is the unit circle. It's 1, right? So I want to be clear about something, that this distance, which I'm going to call y over 1 is equal to what? It's also the hypotenuse, right, of the larger triangle. Is equal to what? So this side over this side is equal to this side over this side. Opposite over hypotenuse. Is that okay? That's what happens with similar triangles. That the ratios of corresponding sides are equal. So y equals the opposite over the hypotenuse. But oh my goodness, what is y? What's the y coordinate called? What's the y coordinate of the unit circle? That's sine. That's sine. So the sine of theta is opposite over the hypotenuse. For the same reason, the cosine of theta is the x value over 1, but that's just the adjacent over the hypotenuse. Adjacent over the hypotenuse. I want to be clear about something. This is our first chance to be relating sides of a triangle to the angles. So not only are we talking about sines and cosines in terms of waves, but if you have a triangle and you know some of the sides and you know some of the angles, you better be talking about trig functions. You better be talking about sine or cosine or tangent or cotangent. They have to come into the picture in order for you to relate angles of one triangle to its sides. That's why they're called trig functions. When you arrive at an exponential function, 3 to the x equals 15, and you want to get x by itself, what do you have to use? If I have 3 to the x equals 17, I need to get that x out of the exponent, what would you use? The log, right? When you come across a triangle and you got some sides, you need to find an angle, you need to use trig functions, right? So again, I'm bringing these functions to you because in calc, you will be needing to solve for x. When you have an exponential function, it's log. When you have a triangle, you're looking for some sides and angles, you need to use some trig, right? All we're doing in this space is creating tools to use with functions, okay? Let's see how that happens, right? So let's summarize. We've got that the sine of theta is the opposite over the hypotenuse. Oh my God, I love this black color. I don't know why I use any other color. Cosine is adjacent over hypotenuse. The tangent is the y over the x, right? So it's going to end up being opposite over adjacent. You can demonstrate that. Cotangent is the x over the y, which is the adjacent over the hypotenuse. You can demonstrate that cotangent is just the tangent flipped. You can also demonstrate that cosecant is just the sine flipped. It's hypotenuse over opposite. And that secant is just 1 over the cosine, which is hypotenuse over adjacent. We define these in terms of right triangles. The coup de grace, the home run, is to be able to do this for any triangle, whether it has a 90-degree angle or not, right? That's called chapter 8, okay? So chapter 8, we will destroy any triangle that dares come our way, right? For the moment now, every one of these triangles is going to have that big old 90-degree angle in it. That's fine, right? But eventually, we'll be able to solve any triangle if you give me 2 sides and an angle, 2 angles and a side, and so forth. Here's an example. 32 degrees, x, 7. And here's what we're talking about, right? We're talking about the power of angles, that somehow, if you give me a triangle, right, and this is what is going to allow us to find almost any distance. If you can make a triangle, you can find the distance. This is what we're saying. If you can make a triangle, find one of the sides, and you know one of the angles, then you've got the whole thing. Now we got this whole protractor thing, right? We can make angles pretty easily. And this gives us an idea of how powerful the angle is, right? By knowing the angle, we can figure out all the sides, okay, and all the angles. I want to know every side and every angle to this triangle, okay? Let's get x first. Here it is, right? I need to find a way of relating this angle, its opposite side, and the hypotenuse. What function is that? Sine. Sine is going to be the way to relate these 3 things. The sine of 32 degrees is the opposite side over the hypotenuse. Yes?
So we'll be given like that, and then we'll have to figure out which one of those we have to use.
That's correct. We're about to drill on this now. That's right. I'm going to put them all up, and I want you to tell me which trig function we're going to use. That's right. That's right. I'm solving for x. I need to get rid of the 7. I'm currently dividing by 7. In order to get rid of it, I need to multiply. X is 7 the sine of 32 degrees, and we're all in the calculator now. Let's practice. As you might imagine, the calculator has two separate modes. Sometimes we're going to be dealing with triangles in which we need to be in degrees. Sometimes we're going to want to know the distance around the track. We're going to need to be in radians, right? And these TI things, you need to go to mode. Yep. Go to mode. Make sure we're in degrees. Go down. Switch that to degrees. Yeah. Make that degrees, and now clear. And now you can do 7, the sine of 32. MyMathLab usually just wants you to round to 1 decimal place for these distances.
4? So what will be 4?
1 decimal place. 3.7. 3.7 feet, 3.7 miles, 3.7 whatever. Okay.
How long can you use that?
Say it again?
I mean, I'm about to say, I use it in chemistry.
Use this in chemistry? Okay.
I don't want to use it.
Okay. So people are getting roughly that this is 3.7 units or whatever, right? We should be clear that sine, are we good?
Is it 3.71?
Yeah, but usually I was going to say MyMathLab only wants 1 decimal place. Yeah, so it's 3.7. But yeah, but just be careful which one they want. But usually I've seen them only use 1 decimal place. While we were talking about units, let's be clear. Sine, cosine, tangent, none of these things have any units. Why not? Why aren't there any units? If I give you a triangle that's in, suppose this was feet. This is feet. This is feet. Right? What's sine in? Sine doesn't have units. Why? Because it's x feet over 7 feet. What happens to the feet? They cancel out. Right? So sine has no feet. So when you look at the units of x is equal to 7 feet times something that has no units. This is in feet. So it just makes sense why the units still work out. Okay. That's the same reason why pi has no units, right? Pi is the ratio of the circumference to the radius, right? And so, I'm sorry, the circumference to the diameter, right? So if you take the circumference, that's in miles, divide by the diameter, which is also in miles, then there are no units. Pi also has no units. Okay. All right, great. So there you use sine. I can't really fool you. I'm going to give you all sorts of triangles, and I'm going to tell you which trig function we're going to use, or you're going to tell me which trig function to use. All right, here we go. Right triangle. I'm going to give you this angle is 27 degrees. This angle, that's size 5, and I have no clue what that is. That's right. I need a trig function. First of all, I look at this, I'm like, wow, okay, I need a trig function. That's the first thing. I'm trying to solve a triangle, I need a trig function. What trig function will relate 27 degrees to its adjacent side, 5, and the hypotenuse? Cosine. The cosine of 27 degrees is the adjacent over the thing I do not know. I'll just cross multiply and solve.
Why is it cosine?
Thank you, I appreciate that. We have demonstrated that cosine is the adjacent side over the hypotenuse. And so what I mean by adjacent side is the side that's right next to the angle as opposed to the opposite side. Right? So the adjacent side is the side that's right next to the angle that is not the hypotenuse. Here you cross multiply both sides by z. Z, the cosine of 27 degrees is equal to 5. I don't know what the cosine of 27 degrees is. Whatever it is, it's got to go. I'm going to divide both sides by the cosine of 27 degrees. We'll plug that in the calculator, round to 1 decimal place. 5.6. That is roughly 5.6.
So what we using? We will be using sine and cosine, like how?
Let me show you tangent. Tangent. Got this one. I've got, that's 15 degrees. That's 3. That's x. I need a trig function. This one comes up a lot. I need a trig function that's going to relate 15 degrees, its opposite side, and its adjacent side. Tangent. 15 degrees is the opposite over the adjacent. Opposite over the adjacent. We'll just switch. X is equal to 3 over the tangent of 15 degrees. And then it's all a calculator. Now, notice that in your calculator, cotangent, secant, and cosecant are nowhere to be found because they're just inverses of ones that are already on the calculator. So I could say that the cotangent of 15 degrees is x over 3. X is 3 times the cotangent of 15 degrees, but cotangent is not on the calculator. Tangent of 15 degrees is, so this is roughly, oh, so the answer is 11.2? Good. Feet, meters, miles, whatever the units are. Okay, this is the length. I think the last problem on the homework is some ridiculous word problem. Okay, so trig word problems are just ridiculous stories about triangles. One person is here, another person's there on the other side of a lake. They both look at a place that's 5 miles down the road from this person. They give you an angle for some reason, as if somehow we can create angles, you know, in person. But yeah, and then we can do it. However, let's be clear while we're talking about this. It is the case, again, as I said on the first day of class, that somehow we know the distance from this place to the sun, right? It's 93 million miles. This is solely from trigonometry. That Aristarchus, we're talking about, goes and finds an angle of roughly 89.5 degrees from the sun, and from that, he was able to find the distance from this place to the moon, right? Just because he found the angle. Angles are powerful, okay? So, yeah, I may bring in that derivation next time on how to find the distance from here to the moon. So yeah, it's pretty remarkable. Okay, I think we've got everything. We're gonna hit the homework, burn through the homework, and we'll end. Homework is 5.1. Super quick. An angle is obtuse, acute if it's less than 90. It's a right angle if it is 90. Obtuse if it's more than 90. Straight if it's 180. Okay. 140 is obtuse. Questions?
Dang, a lot of homework.
Say it again?
Yeah.
You think it's a lot?
Yeah.
Power 2?
Right.
Power 2 is 90. Right angle. Find the radian measure of the central angle of a circle with radius 50 inches that intercepts an arc of length s equals 40 inches, 140 inches. Let's not be intimidated by this. S equals r theta. That's what we said earlier, right? The radius is 50. The length is 140, and you're solving for the angle.
50.
What is it?
I mean, close down.
140
50.
over 50, 14 over 5. Okay, so you're just using s equals r theta for that. All right, so, and they tell you they want an integer or a fraction, right? It's pretty straightforward. Degrees of radians, 80 times pi over 180. We're just trying to reduce, what's that, 20? 4 over 9, or pi over 9. So you just do the fraction, whatever 80 over 180 is, they both have 20 in common, and you do the division. They should probably ask us the other way. Negative 390 degrees, nothing changes, multiply by pi over 180. That doesn't reduce that much, does it? Negative 39 pi over 18. I think 3 goes into both of those. Minus 13 pi over 6. Okay, just rotating. They're being nice to us. Pi over 2. What's pi over 2? 90, thank you. Waiting on you. 13 pi over 9. I'm switching that from radians to degrees. You multiply by 180 over pi. What happens to the pi's? Cancel. 13 times 180 over 9. 180 over 9 is 20. 13 times 20 degrees is 260 degrees. Good so far? Same thing for 8 and 9. So I'm going to leave 8 to you. It's just the same thing. 9, 7 radians. Don't be intimidated by it. If it's in radians, you need to multiply by 180 over pi. Right? And so it's just going to be 7 times 180 over pi. And then now they just want you to round to 2 decimal places. All right, so put that in the calculator and round to 2 decimal places. Yeah, so same thing, pi over 180, I'm sorry, pi over 77, that's in radians, so you want to switch it to degrees, multiply by 180 over pi, it's going to be 180 over 77, and again, they want you to round to 2 decimal places. You don't need this at all for this one, the pi's cancel. Which quadrant is 5 pi over 6? All right, so here's where you would just get the circle and get used to this. 5 pi over 6 is in, so you could convert this to degrees if you need to. It's 150 degrees. 150 degrees is clearly in the second quadrant, right? Once you get used to the circle, you'll see where 5 pi over 6 is, and you'll know that it is this one. It's A. That is quadrant 2. I'll take any questions about, there's more. 4 pi over 3. Slightly more than pi. So pi is at the entry point to the third quadrant, and 4 pi over 3 is slightly more than that. What? Third, yes. I love the way you say third. Ted. That's great. Like, who's Ted? I don't know Ted. Third. I love it. Third quadrant. Draw the angle in standard position. Where is negative 3 pi over 4? Where is negative 3 pi over 4? Right, so positive 3 pi over 4 would take me here. Right? Negative 3 pi over 4 would take me there. Right? Yeah. Okay. So again, that's all unit circle. Everyone should print out their own version of unit circle or just pull it up. 19 pi over 6, a little bit too big for the circle we had normally. Again, we do that division we were talking about. 6 goes into 19 how many times? 3. 3 times. Remainder? 1. 19 pi over 6 is therefore, it's 3 whole pi's plus an extra pi over 6. So that means we need to go around 1. Oh, I'm sorry. That's 1, 2, 3, and another pi over 6. That's a little bit too much, isn't it?
So it'll be D.
For sure. 1, 2, 3 pi over 6. Okay. Let's do the division. What quadrant is that?
C.
3.
Yeah. Good. Here's where we're talking about with the reference angle. 675 is too much. Take off a little bit until we get to an angle we like. Is that going to work? 15? Is that just 315? Yeah. That's the reference angle. Right. So if it's too much, then you just need to subtract off to see what angle is going to give you the same place. Right. Here you're going to add.
245.
Is it really? I think it's just 205, brother.
205.
Yeah. So you just add 360 to that. So the term, the mathematical jargon is coterminal, right? That means it's going to end up in the same place as one of the original angles in the circle. Here they give it to us in radians. Go ahead and divide 8 into 25 goes 3 times. Right. Oh, they're not gonna be nice at all, right? So let's go ahead and do it. So it's gonna be 3 pi. What's the remainder? Pi over 8. Yeah. Debating whether to go ahead and just put this in degrees and then put it back in the radians, right? I mean, so you can go ahead, I guess you can do this, right? You can subtract 2 pi, right? It's too much, right? So then subtract off 2 pi. What does that leave you with? 9 pi over 8, right? So that leaves you with pi plus pi over 8. And the question is that between 0 and 2 pi? And it is. It's 9 pi over 8. Right. It's just that you have to do it in radians, which is just ugly, right? So again, if this were in degrees, this would just be over 360, then you just keep subtracting off 360 until you get a number that's between 0 and 2 pi. And all you need to do is subtract off 360. In this case, it's 2 pi. 3 pi minus 2 pi leaves 1 pi. Pi plus pi over 8 is 9 pi over 8, and that is on the circle. That's on the first go around of the circle. Right, so all you're doing is subtracting off 2 pi. Same thing. It's too much. 3 goes into 21 how many times? 7 pi remainder. Pi over 3. Now we just need to keep subtracting off 2 pi until we're good. So 4 pi is not enough, right? So 6 pi, right? Subtract off 2 pi, another 2 pi, another 2 pi. That leaves us with pi plus pi over 3, 4 pi over 3.
Wow.
Same thing here. Instead of subtracting off 2 pi, you would add 2 pi. So then that just becomes a fraction problem, right? That's 140 pi over 70. Ugly 139 pi.
How you get 140?
I need to get 2. So I need this to be 2. The common denominator is 70.
Oh yeah.
Yeah, so I just need it to be 2. So it's 140 over 70 minus pi over 70 is 139 over 140. That is the coterminal angle. Find the length of the arc as on the circle, radius r, intercepted by central angle. They want us to use this thing. I think they give us everything, right? The radius is 5. The central angle is in degrees. And here we are where they give it to us in degrees, yet they want the answer to be inches. So that means we have to change this to radians. Right? So we have to change the angle to radians. 25 degrees times pi over 180. 5 goes into each one of those. That's annoying. 5 pi over 36. So you just reduce this fraction. 25 over 180. I believe it's 5 pi over 36. And then use the formula. So then S equals 5 pi over 36 times the radius, which is 5. 25 pi over 36 is the distance. They want the answer in terms of pi, so that you don't need to round or anything. They want 25 pi over 36. Oh, and then they ask you to round here, and then plug that in the calculator and round. So the only one for this, again, is you're using this formula, and you need to switch the angle to radians.
Same thing, right?
Same thing for that one.
But for feet. So
Express the following angular speed in radians per second, 2 revolutions per second. What's a revolution? That's the whole circle, 360 degrees, which is just, in radians, 2 pi. 2 times 2 pi, 4 pi radians per second. Just switching from degrees to radians. That's it. So that's 5-1. I know that was pretty quick.
So do we have class next Monday?
We do. Yeah, we're gonna move on. So the test is due Tuesday at midnight.
Next Tuesday?
Yeah, the test is due Tuesday at midnight. Again, we have a practice test that's open. There are 2 practice tests that are open. And so you get to practice those as much as you want for no credit. Okay. 5-2. Where are we on time? Okay. 5-2, we'll roll through these, pretty straightforward. We have 2 sides, and we can find the third side, right? 12, 16, how are we going to find this third side? Using the Pythagorean theorem, a squared plus b squared is equal to c squared. 12 squared plus 16 squared equals c squared. I might need your help. 144, 256, 400, 20. C is 20. The game's now over. Right? The sine of this angle, opposite over hypotenuse. Of course, they want us to simplify. 3/5. Cosine is adjacent over hypotenuse.
Do you mind writing the other parts that you're saying, like the
Opposite over. Thank you. I appreciate that.
Thank you.
Opposite over hypotenuse. Adjacent over hypotenuse, and we're simplifying. Tangent is opposite over adjacent. That is the opposite side to this angle, which is 12 over the adjacent side, which is 16. Both divisible by 4, 3/4. Or you could have just taken this number over that number and canceled out the 5s. Cosecant is simply 1 over the sine. So you just flip the sine. So whatever the sine was, 5/3. Secant is 1 over cosine. So it's 1 over cosine, so you just flip the cosine. That is 5/4. And cotangent is 1 over tangent. Tangent was 3/4, and this is 4/3. So once you have one trig function, you have them all. Specifically, once you have those 2, everything else just comes out super quick. Please, go ahead.
Can you show me how to do the opposite hypotenuse and the adjacent one more time? Like
Thank you.
Triangle?
So here's the angle right here.
Yeah.
The side opposite it is 12, right? The hypotenuse we found was 20. So it's 12 over 20. Is that what you were asking?
Like, I just want to know the opposite hypotenuse and adjacent on the triangle. Like, how can you find it?
Oh, okay. So first of all, they're going to be referencing an angle, right? So here's the angle theta, and the way that you get the opposite side to the angle is the side that's not touching the angle.
Okay. So,
Right.
all right.
Yeah, so that's why it's 12. And the adjacent side is the one that's right next to it that is not the hypotenuse.
All right.
Yeah. Thank you for your question.
Is all of it?
It can't be, right? Oh, we made it into pages. Okay. Same thing?
Snap.
Oh, this is the same question. You crazy? This is the same question. 3 blank 5. What's this side right here? How are you gonna get 5? 5 is hypotenuse, so 3 squared plus b squared equals 5 squared. 9 plus b squared equals 25. B squared equals, someone save me here, b is 4. Right? And you just run them all. Right? The sine of b is this angle. So let's label this now. That's 4, right? So opposite 4 over 5. The opposite of b, not of a, it's of b. So b is the angle of interest. Cosine is 3 over 5. Tangent's 4 over 3. Cosecant is 5 over 4. Secant's 5 over 3. Cotangent's 3 over 4. This all follows from the definition, right? Tangent of 60, we can figure it out from the unit circle. They've given us this nice triangle to mimic the unit circle. Tangent is the opposite over the adjacent, and we just have to figure out that it's this angle we're talking about, opposite over the adjacent. Square root of 3 over 1.
Yeah, next page.
Say it again? Oh, thank you. Cosine 45 degrees, we already know. Square root of 2 over 2, regardless of the triangle, whatever. You can use a triangle if you want. If you use a triangle, it is adjacent over hypotenuse, right? And then you're at that 1 over the square root of 2, stuff we got originally. Do they care? They may actually take this. Okay, so they may not even care that you have to, that you don't, whether you rationalize or not. Either one will work. Cosecant of pi over 4. Cosecant is 1 over the sine of pi over 4. So find the sine of pi over 4 and flip it. We know the sine of pi over 4 is the square root of 2 over 2, so this is just 2 over the square root of 2. So take the square root of 2 over 2 and flip it. This one wants you to rationalize. Okay, so notice the difference in these two. This one says nothing about rationalizing, so that means it's going to take this one. This one wants you to rationalize, therefore it will not take this one. Okay, so then we have 2 over the square root of 2, and then you have to rationalize by multiplying by the square root of 2 over itself. 2 square root of 2 over 2, the 2's cancel. This is the square root of 2. Alright, so just be careful. Alright. So we got an acute angle, and I'm going to tell you that that's sine, that's cosine. Tell me all the other ones. Well, tangent is sine over cosine. So that you would just do 20 over 29 over 21 over 29. What happens to the 29s?
Cancel.
They cancel. Cosecant is just 1 over the sine, so flip the sine. So it's 29 over 20. Secant is 29 over 21. Flip the cosine. 1 over cosine. Sorry. Cotangent's 1 over tangent. And so that's 21 over 20. Questions there? Good. Everyone's dialed in. Same thing, right? So the only thing you have to worry about is just rationalizing. Does it say to rationalize? It does the whole way through. Sine over cosine. So let's see if we have to rationalize here. We do. It's 6 over the square root of 13. You get good enough at these, you'll be able to read this off super quick. Anyone know what this is going to be? 6 square root of 13 over 13. Yeah. Cosecant, you flip the sine. 7 over 6.
So would it be 6?
7 over 6? It's just 7 over 6.
7 over 6.
Yeah, yeah. Secant of t is 7 over the square root of 13. Rationalize super quick. It's going to be 7 square root of 13 over 13. Cotangent is going to be this flipped, but I would almost prefer to just flip that, right? Square root of 13 over 6. I don't have to rationalize anything. This is 1 over cosine, and this is 1 over tangent. Okay. Yeah, it's all good. Here, I got an acute angle. I'm going to tell you sine and not tell you cosine. Okay, but I know that sine squared plus cosine squared is 1. So I'm going to use this, plug it here, and get cosine. Right? So I got 5 over 8 squared plus cosine squared equals 1. 25 over 64 plus cosine squared equals 1. Cosine squared equals 1 minus that. Is that a funky 39? So cosine theta equals plus or minus the square root of 39 over what? The square root of 64, which is 8.
How'd you get 39?
Yeah, so 1 minus 25 over 64. So I subtracted this on both sides. So it's just that fraction. And so yeah, it is 64 over 64 minus 25 over 64. I think 64 minus 25 is 39. All right, is it a plus or a minus? How do you know?
Because it's plus.
You better tell us something about the angle. What's the angle? Acute, so it's less than 90. So what quadrant is that in? The first quadrant. The x-coordinate in the first quadrant is positive. Square root of 39 over 8, and then all the rest of them. Oh, the only one in the cosine. But from this, you would be able to find tangent, cotangent, all the rest of them, right? Identities. The sine of 57 degrees times the cosecant of 57 degrees is, what's cosecant again? 1 over sine, right? What happens there? And you're left with questions? Good. They cancel, right? Secant and cosecant cancel. I'll go back. What page was that? I don't think it was 4. It was 4. Sine squared plus cosine squared is, what is it? 1. For any angle, doesn't matter how bad the angle looks, sine squared plus cosine squared is 1. Always, always, always. Okay. All right, so we haven't talked about cofunction identities, cofunctions. All right. So I have yet to fully graph these things. I've graphed sine. Cosine is going to be similar. Let me go ahead and graph them together. So here's sine. And we're going to spend a lot of time looking at the graphs of these. There's cosine. And the thing to notice is that they are exactly the same graph, except one is shifted just a little bit more than the other. Let me take this one home to the origin. Which one is sine? The red one, right? Sine goes through the origin. The sine of 0 is 0, right? At 0, you get 0. So cosine is the 1. At 0, you get 1. Notice again that sine squared plus cosine squared also always has to be 1, so that if the sine is 0, then that means the cosine has to be 1 or negative 1. Okay. The other remark, again, this is pre-calculus. The other remark we should notice is that whenever the sine is going up, did I already even say this? Whenever the sine is going up, the cosine is above the x-axis. And the moment that sine starts to go down, the cosine becomes negative. If you want to know how the sine is changing, the cosine will tell you, right? In calculus, that means that the derivative of sine is cosine, whatever that means. but in calculus we care about the rate of change. And so sine and cosine are very much sibling functions in this way, that they say so much about the other thing. Okay. So, sine will also tell you about how cosine changes, but in a slightly different way. I mention this only to say, I put these two graphs up only to say that the reason why we call this cosine is because this is just the complement of this. If I shift this by 90 degrees, I get the other one. Right? So if I do, what's 90 degrees in radians? Pi over 2, right? So if I shift this, they're exactly the same thing, right? So that the sine of x is the cosine of 90 degrees minus x. Right? What does this mean practically? This means that, and so that's what cos stands for. Cos stands for complementary. Two angles are complementary if they add up to 90 degrees. So what does this mean? This means that the cosine, or I should say the sine of 43 degrees is actually the cosine of 90 minus 43 degrees. Right, so it's the cosine of 57. You can test that with your calculator if you like. That if you have the sine of one angle, if you take the cosine of the complement, you get the same thing. Okay. And so that's why it's called cotangent, and that's why it's called cosecant, because the tangent of pi over 9 is equal to the cotangent of pi over 2 minus pi over 9. And you just have to play with the fraction. So if I wanted to know the sine of 25, that's equal to the cosine of, what's going to give me 90? 90 minus 25, right? Cosine of 65 degrees. Cosine of 65 degrees. You would put it there. Right? So you would pick E. Co-function is. Rest is calculators. Put it in degrees. Sine of 20 degrees. What is sine of 20 degrees? Rounded how many? That's 4 decimal places is not a joke. Sine of 20 degrees. Say it again. 0.342. You sure it's 0?
Yeah.
Perfect. Put it in radians. Cotangent of 3 pi over 8. Cotangent is not in the calculator. 1 over the tangent of 3 pi over 8. And the TI calculator goes 1 / parentheses. I don't even think you need parentheses. Tangent, parentheses, 3 pi button /8, close parentheses, close parentheses. 1 over tangent. What do we get? Say that again? 4. 48.6273.
Yeah, that's wrong with what it's saying in here, but that's the same answer I got.
Why do you think that's wrong?
The sheet on your answer key says it's wrong.
Oh, what do they have?
0.4142.
Are you in? Did you switch your calculator to radians? You switched to radians. Oh, so that's what we have to be careful about, right? Make sure we're in radians. This? Okay. All right. So good. So radians. Remember. Okay. All right. And this is all the stuff where we left off before. All right. So I'm going to leave these to you. I just need you to tell me which trig function are we using. I need to find what A is. Trig function that relates an angle to its opposite side and the adjacent. Tangent. The tangent of 35 degrees is A over 340. Multiply both sides by 340. Looking for B, an angle and its adjacent and hypotenuse. cosine. The cosine of 55 degrees is the adjacent over hypotenuse, multiplied by 109 and round. Oh, here, now remember, they want the nearest whole number, not one decimal place, which I thought. Make sure you're in degrees. C, opposite hypotenuse, sine, 36 degrees, opposite over hypotenuse.
So you divide both sides.
So you just switch? Yeah, that's right, 24 over the sine of 36 degrees. Be in degrees, and put the nearest whole number. All right, final thing on the calculator, I think. I got the cosine of theta equals 0.8922. I want to find what theta is. It's the inverse cosine of 0.8922. All right, so there's an inverse cosine button on your calculator. I just want you to use it. Round to 3 decimal places. Inverse cosine of 0.3223. So that sometimes you won't know the angle, right? So all those examples I gave earlier, you had the angle. What if you don't have the angle, right? So you apply the inverse symbol for that. We'll talk about those next time, I'm sure. Silly word problems. No difference. You don't even need to almost read this thing. Which trig function are we looking at? 36 degrees. I don't know the opposite. I do know the adjacent. That's tangent. Tangent of 36 degrees is A over 640. Here I don't know the angle. Find the angle to the nearest degree. What trig function relates this angle to its opposite side in the adjacent? Tangent. So here we go. Tangent of theta is 129 over 148. The way that you drop this tangent is by applying the inverse tangent. All right. So on the TI calculator, you press second and then tangent. It creates tangent inverse, and then you just put in 129 over 148. There's nothing that's going to stop us in any of these problems. 4 degrees, 500, which trig function? Sine. The sine of 4 degrees is 800 over C. And this is precisely what I meant about destroying the triangle, right? There's nothing, there's no right triangle that they're going to give us in which they give us an angle and a side, and we won't be able to find every angle and every side. 23 is this one? Nope, nothing. All right. Well, in there, that's the homework. I will post this.